All right, ladies and gentlemen, class recording has started. So, the past 3 units, we have been dealing with our introduction to mechanics. We said mechanics is the study of motion. And there's questions that we want to answer, right? Where is the object? What is it doing? What's it going to do next? When are all these things happening? Why is it changing what it's doing, right? And that gets us into the idea of displacement, velocity, acceleration, force, all those things. And then in the last unit, we talked about energy. And we said that energy is just a different way of describing all of those things that we've talked about previously. We're still talking about how fast, and we're still talking about where an object is, but now we're just describing it from a different standpoint, right? And we talked about the idea that a lot of the problems that we did in the last unit are similar to problems that we did previously. We just adjust them from a different standpoint. So this unit takes the mechanics idea and takes it one step further, takes the dynamics idea, dynamics is forces, and takes it one step further. When we talk about the ideas in Newton's laws, we said there are basically 3 factors that we look at to describe the changing of the motion of an object, right? What are the 3 things that Newton's laws deal with, basically? Acceleration. Inertia is measured by what tells us how much inertia something has. What tells us how hard or easy it is to get something to move. Mass. Right, so acceleration, mass, and force, right? Force, mass, and acceleration. Those are Newton's laws, basically, right? That's what Newton's laws deal with. How do we change the motion of an object? What do we have to do to get it to change? How much does it change, et cetera, et cetera. And we talked about that force and acceleration are directly related, right? More force, more acceleration. And that mass and acceleration are inversely related. More mass, less acceleration, or vice versa. But there's a couple factors that we also have to include in there, and that's what we get into in this section here. All right? So, these 2 pictures, which you guys have on your sheet as well, illustrate one of the ideas that Newton knew was going on, and we'll actually see that he actually addressed these ideas when we talk about his second law in a little bit more detailed form. So, this picture on the left of a guy standing on a skateboard, and this girl throws a big heavy object, he catches it. If we assume that the wheels on the skateboard are really, really good and not, let's say, friction-free, but very friction-small, right? Okay. When he catches this big object, what's going to start happening? It's going to roll backwards, right? But, now let's go with the one on the right. On the one on the right, same guy, same skateboard, different object though. And you can kind of tell from the arrows, the green arrows are representing velocity, okay? This big object has a small green arrow or a short green arrow, and this smaller object has a much bigger green arrow, right? Representing that that smaller object is being thrown much faster. If the guy on the skateboard catches that smaller object, he'd still start moving backwards. And what they're trying to show you here is that we can make that guy move backwards with the same velocity by throwing him a big object or a small object. But what else plays a role in that? The velocity as well, right? That how fast we have that object does play an effect on what happens when it interacts with other things. Hannah, go ahead. Yes, very much so. That we get into that same idea. Some of those, Hannah asked about, does it get into the idea about smaller force, more work? If we but there's also a distance factor there, right? That work is force and distance. So we have to get into that. We talked about, excuse me, catching the water balloon, right? If you catch it with your hands flat and it hits and it breaks because there's a large force over a very short distance, right? Those ideas are going to come up again and again. That's basically an inverse relationship. We're going to see that as well, okay? So, this idea that when we're describing an object and its motion, we have to take into account not only how big it is, but also how fast it's going. That gets us into the property of momentum, right? So the momentum of an object is defined as m times v, its mass times its velocity, okay? Now, like it says here, because momentum is the product of mass and velocity, an object's momentum changes whenever its mass or velocity changes. Duh, I hope that, as far as the unit goes, and you guys got into this a little bit with your lab last week, okay? All we do with the unit is just sort of mash together the two units for mass and velocity. So kilograms times meters over seconds, or if we write it IB-wise, it would look like that, okay? That one doesn't have any special units, it's just, that's how we define it there, okay? Good? Big thing about momentum that we have to keep in mind, that's a little bit different from the last chapter, is that momentum is a vector quantity because it deals with velocity. Now, when we talk about vector quantity, right, the one thing that we include there is the direction. And we talked about, like, for a car driving on, in last unit, we talked about kinetic energy. We said it doesn't really matter which way a car is driving. It'll get into an accident and cause damage regardless if it's going west or going east, all right? But if a car is going west and runs into, let's say, a telephone pole, right? I know that's not nice to think about, but, right? If it's going west and runs into a telephone pole, that telephone pole will follow a certain direction. If it's going east and runs into a telephone pole, that telephone pole is going to fall in a different direction, right? So there is an importance in direction there when we're analyzing what happens when this object interacts with other things, right? So momentum and velocity are related in that momentum is a vector quantity. If we have this situation right here, right, we have a beanbag bear and a rubber ball, okay? If we drop the both of them, we know that on the way down, they should accelerate at the same rate, right? And when they get to the ground, they should be going the same speed because gravity accelerates them all the same rate. But when they hit the ground, obviously two different things happen, right? The beanbag stops, but the ball will go back in the other direction. And let's say this was a perfect collision or perfect interaction between the ball and the floor. No energy was lost to heat. How fast would the ball be going when it leaves the floor versus when it got to the floor? Same. In real life that doesn't happen, but let's say that it does. But the motion of the ball on the way down is different than the motion of the ball on the way up, right? So there has to be a way to distinguish that. That's the velocity, right? That's the vector part of velocity, but that then carries on to the momentum as well, okay? Good there? So momentum is the product of mass and velocity, but those are both, momentum and velocity are both vector quantities, so the direction is important, and we'll see why that is in just a second. Okay? Hi, go ahead. Yep.
There's a bear. Isn't there like weight, like kind of just, isn't it distributed usually, like mass? Because like it's a beanbag.
It is, although when we're talking, to start off with mechanics, right, the way that the mass is distributed there, at the beginning that doesn't make a whole lot of difference, right? We're just going to talk about it basically being a dot, you know what I'm saying? At the end, and that gets into, that is one of the reasons why a ball bounces but the beanbag doesn't too, which the way the way it's distributed a little bit has to do with the interaction when it gets to the floor and when it leaves the floor and stuff like that. So let's not get too much into that right now because that's much more complex than we want to start off with at this point in time. But for our purposes here, let's say no, that really doesn't make a difference. Let's say it's uniform, okay? Or let's say instead of a beanbag, maybe it's a stuffed animal that doesn't have that kind of distribution difference, okay? All right, good there? Okay. Because momentum is a vector, right?
That's that.
What?
That's come.
What?
That's come.
What
That's
is?
come.
Oh. Yeah, you get into this when you do like ideal
We
gas
did,
law and
we
stuff
did
like that.
that.
Right? Because momentum is a vector, when we talk about multiple objects, we have to find the vector sum. Now, if we start in one dimension, a straight line, all we have to do to determine the direction is positive and negative, right? That if we talk about this problem with this goose and these ducks, and I won't go through it right now because I just want to get our numbers first, or want to get concepts first, okay? If we talk about this goose swimming this way, these two ducks swimming that way, right? They would have different momentums. One would be positive, one would be negative, because we have to get the vector nature of that. When we're finding the total, right, vector sum in one dimension, we just take the positives and subtract the negatives. But when we talk about two dimensions, right, if we have something going this way, right, and something going this way, they both have momentum. Those are both vectors, right? But that's when we would have to start getting into then, right? That's when we have to start getting into like the idea of finding the vector sum through Pythagorean theorem and stuff like that, right? So those kind of things will come back. When we're dealing with work and energy, it really doesn't make much of a difference. Okay? Good there? Now, momentum's great, but Evan, we came up with that, you kind of threw out the idea of inertia a little while ago, right? If what inertia is saying is that the momentum of an object would never change on its own, mass, velocity, right? The mass of an object never changes. The velocity of an object doesn't change unless we make it change, right? And so momentum would never change if we didn't make it change. Does that make sense? So the next part of this section deals with impulse. All right. Getting back a little bit to what you talked about before with the force and the distance, right? At the beginning here, they have a little description of a situation that might happen in the parking lot of the grocery store. Okay? Let's say you're at the grocery store with a little cousin or a little brother or something like that, and they want to push the cart full of groceries back to your car to get it filled up, right? They can apply a force to that cart, right? It's probably a little bit smaller of a force than you could apply, right? Eventually, they would get that cart back to your car. But what's the trade-off of the smaller force? It would take a longer time, right? You could accomplish exactly the same thing in a shorter amount of time because you can apply a greater force. So when we talk about how much an object changes, we have to address what the force is, but we also have to address how long that force is applied. We call that quantity the impulse that is imparted on an object, or the impulse that is provided to an object, right? So the impulse is the product of the force and the time over which we apply that force, right? We learned back in 2 chapters ago that if we apply a force to an object, what's going to happen to it? It's going to accelerate. And if it accelerates, its velocity changes. And if we now know that if its velocity changes, what else will change? Its momentum. So, impulse is a product of force times time. But more importantly, an impulse changes an object's momentum. So the impulse that we provide to an object causes a change in that object's momentum. And we refer to that idea as the impulse momentum theorem. All right? Simply put, the impulse that acts on an object is equal to the change in the object's momentum. Okay? This is actually a restatement of Newton's second law. Watch. All right. Newton's second law, yes? Yeah? Newton's second law is F equals ma, right? All right, good there? Now, acceleration. The acceleration of an object depends on two factors. Do we remember what the two factors are? Change in velocity over time. So, delta V over T. Yes, that's a V. Okay. Rearrange a little bit. And we end up with that. Okay? Left-hand side of the equation, force times time. We just learned that that's called what? That's impulse. Right-hand side, it's m times v, but it's not just m times v, it's actually m times change in v, which is a change in the momentum, right? The impulse momentum theorem is basically just Newton's second law, but now we've added in this time factor, because that's important, right? If we have a rocket, the rocket has a huge engine as it sits on the rocket on the launch pad. It has a huge engine. If we fire that rocket, a large force will be imparted on that rocket. But if we only fire the rocket for 1 second, is the motion of that object going to change very much? Right? How long we apply the force is important. Okay? Good with that idea? All right. So, let's take a look at, which one do I want to do? Yeah, we can do this one. Well, yeah, let's do this one first. I know it's at the very, very end, but we'll go here. Okay. All right. So it says, 3 friends push a stalled car and its driver to a nearby service station. Assume that the car rolls without friction on a smooth and level road. If the car is initially at rest and 3 students give a combined push of 305 newtons, what is the momentum of the car and the driver after 12 seconds? So, when it says, what is momentum of the car and the driver after 12 seconds? When we throw after into our description, what is it asking us about? Kind of. If it's after, it's actually more specifically asking us for what? Final, right? Does that make sense? Okay. But in this case, it's not final velocity, it's actually final what? Momentum, right? So, did we go over before? Momentum is P. I showed you guys that before, right? So okay. I know. So sometimes you have to do that, okay? So we use the letter P to represent momentum. The reason being that when the idea was being developed, basically by Newton, they kind of referred to it more as progress as opposed to momentum. That's kind of where the P comes from, right? So it says, what is the momentum of the car after 12 seconds? So then that also gives us a time factor, right? A little bit earlier in the problem, they told us 2 things about this car, right? If the car is initially at rest, okay, that gives us an initial velocity, but it also gives us an initial what? Momentum as well, right? So we know now that the initial momentum has to be 0, because regardless of what the mass of the car is, if its velocity is 0, it has no momentum. And then 3 students give a combined push of 305 newtons. That's going to be our force. Okay? Good there? We just learned that according to the impulse momentum theorem, impulse is equal to the change in momentum. We also just learned that impulse is force times time, and we know that if we're going to change the momentum of something, we ought to go final minus initial, right? All right. we know that the initial momentum of this car is what? 0, so this term just goes away, right? And that the final momentum of the car is going to be equal to the impulse that is provided to it. Impulse is just force times time, right? So it should be somewhere, doing this in my head, right? 420? Come out that way? Do we know what we're doing, by the way? Force times time, right? Because that's the impulse that we've provided to that object. Okay. I know. Oh no, sorry. 4,200. 4,000. Okay. Okay, so units for this. There's 2 ways we can go here. Okay? Force times time, the unit for force is newtons, the unit for time is seconds. Okay? So that we can just go force times time like that. Or we know that newtons is actually its own derived unit. That's our derived unit for newtons. Okay? If we multiply that times seconds, right? That would cancel, and we'd be left with this, right? Yeah, you can leave it newtons, not newtons per second, newtons times seconds, right? But then we're left with this, which just so happens to be the unit for momentum, which is important because impulse causes a change in momentum. So just like work in joules, work in energy, they have to have the same unit because work is a change in energy. Impulse and momentum have to have the same unit because impulse is a change in that momentum. Right? Technically, momentum could be that as well, right? Yeah, because those cancel out the way that they cancel out and they leave you with this. So yeah, momentum and impulse have to have the same units regardless of what it is. Right? So, going back here, right, okay, we go, that's a 3, sorry. All right, good there? And then for part B, right, if the mass of the car and the driver is 1,360, what is the car's velocity? So for part B, they want final velocity. We know that the final momentum is 3,660 Newton seconds, or kilograms times meters divided by seconds. And they gave us that the mass was 1,360 kilograms. All right. Ooh. Okay. So to find the final velocity, we're just going to do what? Momentum is equal to m times v, right? If you know p and you know m, right? And we should end up with somewhere around 3. We should probably go with 3 sig digs, right? So. Okay. All right. Good there? All right. Let's see. Okay. So we just did a problem where we looked at the change of momentum and how it equals impulse. One of the things that we talk about, and you guys saw this in your lab last week, if we take a situation where a guy hits a baseball, right? Ball's coming in this direction, ball's going out in that direction, okay? Momentum-wise, that's a big change because momentum is a vector, right? Momentum in one direction and momentum in the other direction are, even if it's the same number, those are 2 different momentums, right? So when we apply impulse momentum equation to a situation like this, okay, impulse is equal to final minus initial, right? Let's say the initial direction, we call this the positive direction, and that's the negative direction. Okay? Good there? When we go final minus initial, this would be a negative number minus a positive number, right? Even if we're talking about the same value, the same magnitude of the momentum, right? When things bounce, this is actually twice as big of a change. Does that make sense? Right? Negative minus a positive gives us twice as much negative, right? Even if we had flipped these around and called this the negative direction and called this the positive direction, right? When we do final minus initial, we have positive minus a negative, right? Okay. And when we do that, that actually gets us twice as big of a number. Okay? So keep that in mind when you're doing your calculations on your lab from last week, because when you have to calculate the change in the velocity, right, those are vector quantities, and you guys wrote down that some were negative and some were positive, or at least you should have, right? And that plays a role when we're calculating out the change in the momentum. Okay? Good there? All right. For tonight, if you take a look at the calendar, there are some homework problems dealing with concepts of impulse and momentum. So I don't think there's any calculations here. I think these are all straight concepts, or if they're calculations, they're kind of simple ones like the ones that we just did in class today. Okay. I haven't put the answers up yet, but I will today because my freshmen are taking a test, so I'll get the answers up there. Okay. Also, you should be able now to do all the calculations and answer all the questions from your lab that we did last week. Okay. Tomorrow in class, we will do some applications of these ideas. I do want to do, I don't know, I think most of you have kind of smartphone that you can get on the internet in class. Yes. Okay. I do want to do an activity where we're actually going to do some interactive stuff up here on the board. What? We are going to do Kahoot. Yeah. So I've actually done another one called Poll Everywhere, but I kind of like Kahoot better because it's like it's an interactive website where it's like a quiz. I'm gonna give you stuff up here on the board, and you're gonna like vote for your answer. And it's kind of like if you ever done trivia at like BW3s, like yeah, it's kind of like you guys get to give yourself a name up on the board, so you can like. That's not makes sense. Wait, is this tomorrow? Yeah, we're gonna do that tomorrow. So if you don't usually bring your smartphone with you, bring your smartphone with you tomorrow.